what actually happens when no net force acts on an object. Lucky and I would like to start again from the very beginning in this video and take a closer look at the simplest case in mechanics. If you understand this simple case well, it will be much easier later to understand what changes when forces and accelerations come into play. Because this is where the terms appear that will come up again and again later: position, time, velocity, and equations of motion. Welcome to Physics with Lucky. Today we are talking about uniform motion, and that is simply motion with constant velocity. The topic is actually quite simple, but that makes it all the more important to really internalize it. So today we want to make everything very visual, and we start with a small experiment. We imagine a road and place a small marker every 5 meters. On this road we place a nice vintage car. Then we also need a stopwatch. The experiment works as follows. In a moment, we let the car start moving, and at each marker the car passes, we measure the time and enter the position and the time into the table in the upper left corner. At the beginning, at t equals 0 seconds, the car is at x equals 0 meters. Okay, here we go. Wonderful. We now have our measured values, 6 time values and the 6 corresponding positions. Now let us take a look at the distances delta x that the car traveled between the measuring points and at the corresponding time intervals delta t that passed between these measuring points. Delta t is the difference between one time value and the previous one, so t2 minus t1 or t5 minus t4 and so on. The same applies to delta x. That would be, for example, x1 minus x0. As you can already see in the sketch, although you could also calculate it, all delta t intervals have the same duration, namely 10 seconds. And the same is true for all delta x intervals. In our example, all distance intervals are 5 meters long. And that is already the core idea of uniform motion. The same distance is covered in equal time intervals. And that brings us directly to the definition of velocity. The velocity v is defined as the distance covered per unit time, so delta x divided by delta t. This is why velocity always has units such as kilometers per hour or meters per second. In our example, that is 5 meters in 10 seconds. If we divide 5 by 10, we get a velocity of 0.5 meters per second. If we multiply this value by 3.6, we get the velocity in kilometers per hour. So that is 1.8 kilometers per hour. Okay, pretty slow for a car, actually very unrealistic, I know. So yeah, but this example is my fault, so Lucky is not to blame. Okay, for the next insight, we start with the formula for velocity that we just introduced. Delta x divided by delta t. We can easily rearrange this formula for delta x. However, the goal of the following exercise is to find a function x of t. We can insert any point in time t into this function and directly calculate the position of the car at that time. This may be a little challenging, but stay with me, it's worth it. The result is very simple again, and afterward we will also visualize it a little. Let's do this step by step. We already know a few values of this still unknown function x of t. The value of x at t0 is x0. In our example, that was the starting point at 0 meters. The value of x at t1, so x1, was exactly 5 meters, meaning 1 delta x farther to the right. The value of x at t2, so x2, was again 5 meters farther to the right, so in total it was 10 meters farther than x0. And the value of x at t3 was another 5 meters farther to the right, so in total 3 times delta x farther than x0. So we can immediately see a pattern. The value of x at a time ti is x0 plus I times delta x. That makes sense, right? In our example, x0 was 0 and delta x was 5 meters. If we insert these values, we get exactly the xi values from our example. And now comes the important step. Now we insert the rearranged formula from the upper left instead of delta x. Delta x was equal to v times delta t. And that already looks almost like what we are looking for. So let us keep this for now. Now I want to get rid of the product I times delta t. But what exactly is I times delta t? Well, I times delta t is exactly ti. For example, t3 was at 30 seconds. And that is exactly 3 times delta t. And it works like this for all ti. Feel free to go back and check again. So we replace I times delta t by ti. And that is basically already the final result. I just still have to get somehow rid of the index I. Lucky says that since there is no delta x and no delta t left in the equation is completely independent of our original division of the distance or the time. We would always get exactly the same equation even if we made the intervals arbitrarily small. This means that this equation is valid at every position and every time. And I could not have explained it better, so here it is. The position-time equation for uniform motion. You should remember this one. Since the position-time equation gives the position as a function of time, it makes sense to plot this function in a position-time graph. At t equals 0, the object is at x0. This is its starting position. And then the function increases linearly with time. The function currently shown is obtained when the starting position is x0 equals 1 meter and the velocity v is 1 meter per second. In our example from earlier, the starting position was x0 equals 0. In that case, the graph passes through the origin of the coordinate system. If the starting position is a little farther back, for example at 3 meters, then the graph is shifted upward accordingly. But let us set the starting point back to 1 meter. What happens now if we reduce the velocity, for example to 0? In that case, the slope of the function changes. And if the slope is 0, the function is constant. So the position remains the starting position for all times. The object does not move at all. If, on the other hand, we increase the velocity, then we increase the slope, and further positions are reached in less time. Exactly as we would expect. Feel free to subscribe to the channel if you do not want to miss more explanations like this. Let us now summarize our results. For uniform motion, the position at any time can be calculated with the familiar function x of t. The velocity is constant for all times, and it is equal to the initial velocity. And there is no acceleration, so the acceleration is 0. And this is equivalent to saying that no net force acts on the object. Because if the force F is 0, then m times a must also be 0, and that only works if the acceleration vanishes. Yes, Lucky, or the mass. And that's it for today. And this is Lucky in uniform motion with v0 equals 0, and very tired. Leave him a like, he will be happy about it later when he wakes up.